A neural network can make a prediction. But making a prediction is only the beginning. The real challenge is figuring out how to improve the network when that prediction is wrong. The story begins with forward propagation. We send an example through the network. The network produces an output. Then we compare it with the correct answer using a cost function. But how do we tell every weight and bias how it should change? The answer is backpropagation. We start at the output and work backward through the network. Using the chain rule, we calculate how each parameter contributed to the error and move backward through each layer. During forward propagation, the network already calculates many of the values we need. So we store them in a cache and reuse them during backpropagation. This makes training more efficient. Once we have the gradients, gradient descent updates the weights and biases. And the network tries again. But backpropagation alone doesn't guarantee a good network. The activation function also matters. Sigmoid produces values between 0 and 1, making it useful for classification. But when its input becomes very large or very negative, its gradient becomes very small. This can cause the gradient to vanish. Tanh can face a similar problem. ReLU behaves differently. For positive inputs, its gradient is 1, allowing gradients to flow more easily. That's one reason ReLU became widely used. Initialization matters too. If all the weights start the same way, neurons can learn the same thing. This creates a symmetry problem. Random initialization gives different neurons different starting points, allowing them to learn different features. Normalization can also help. If inputs are too large, they can produce very large values inside the network and cause activations to saturate. So we can center the data around its mean and scale it using its standard deviation. This can make training more stable. But deep networks still face another challenge: vanishing and exploding gradients. As gradients move through many layers, repeated multiplication can make them extremely small or extremely large. If they vanish, earlier layers barely learn. If they explode, training becomes unstable. Proper initialization can help keep these values under control. Techniques such as Xavier and Glorot initialization were developed to help with this problem. Now we have another question. How should we optimize the network? Batch gradient descent uses the entire dataset for every update. Stochastic gradient descent uses one example at a time. So in practice, we often use mini-batch gradient descent. We divide the data into smaller batches, calculate the cost, backpropagate the gradients, and update the parameters. This gives us a balance between efficient computation and frequent updates. Researchers also developed momentum. Instead of considering only the current gradient, momentum also considers previous updates. This can help the optimization process move more efficiently toward the minimum. And that's the journey. Forward propagation produces the prediction. Backpropagation sends the error backward. The chain rule connects the gradients across layers. Caching makes the process more efficient. Activation functions help the network learn complex patterns. Initialization and normalization help make training stable. And mini-batch gradient descent with momentum helps optimize the network more efficiently. But training a model is still only part of the problem. Even after building and training a neural network, how do we know what's actually going wrong when it performs badly? How do we identify its biggest mistakes and decide what to fix first? That's exactly what we'll explore in the next video. Debugging ML models and error analysis.